Hi everybody, I'm Steve. I'm here to give you this talk with this terrible or awesome pun, depending on your opinion. The talk you've been awaiting for. I work at Cloudflare and some stuff totally unrelated to all these things, but before that I worked at Mozilla on the Rust programming language, and I'm still working on the Rust language in a hobby capacity these days. So I've been on the core team since like 2014, and I wrote the book, The Rust Programming Language, if you're trying to learn Rust. And so this is kind of a talk that I've been really super psyched to give for a very long time. And it's about how Async-Await works in Rust at like a very deep sort of technical level. So come on, speaker notes. There we go. So this is a screenshot from this blog post. This actually happened last week. Yeah, last Thursday. We released Async-Await in Rust. And this is a culmination of like 4 years of development, maybe 3 or 4 years in total. And it was the work of a lot of people, all of whom were not me. So one of the functions I like to play in the Rust world is like amateur historian. So I sort of like to collect what we've been doing and then present it to people. So I want to make it super clear that I didn't do any of the work to design this feature. I'm just here to explain it to you. And I have some citations. This talk specifically draws on some really great blog posts written by some of the people who did do all of that work. And so I have some links at the end. And you can also go read a bunch of that stuff. But yeah, so previously at QCon, I gave a talk called Rust's Journey to Async-Await. I should have paused it on my title slide and not like QCon New York, but whatever, it's fine. That talk was given like about a year ago, and it was a very high-level overview of like why Rust cared about Async-Await and an overview of different concurrency methods. And so if you want like a high-level version of the talk, you can like watch that previous one. But I'm really excited for this now that we've actually shipped the feature to talk about the low-level details. This talk is sort of like, we're going to talk about how asynchronous functions de-sugar into more complicated futures, and there is like a lot of code in this talk, and a lot of type signatures. So how many of you have like written Rust before or would think that you're reasonably competent at Rust? Awesome. That's very exciting. For those of you who are not, hopefully you can follow along. I'm sorry if it's a little tough. I'm going to try to take my time and go through things, but there's a lot of stuff going on here, and I really want to get like deep into the nitty-gritty because I think that's really the most interesting part. I picked this image because it's like a meme, but also I think it really fits with the theme of this track because Rust's implementation of Async-Await is in many ways actually kind of novel. It's not novel in the sense that we invented brand new things, but we assembled a bunch of existing concepts together in a way that had not really previously been done. And that's part of why it took so long, but that's also why I think it's really interesting and exciting. And so I think we have the like most performant possible implementation of Async-Await that could ever exist. We'll see if someone proves me wrong someday, but like when you look at overheads and stuff, it's like very, very low. And so we're going to get into how all that works. It involves a lot of moving parts. Fundamentally, we're going to talk about 3 things. And then depending on if I have time, we'll cover one last little bonus round. I usually give talks that are not very code heavy, and so I know how long those are, but this is a very code heavy talk, so I wanted to put a little bit of extra stuff in there. So maybe we'll get to async functions and traits, but the 3 core important things to understand when you want to get into Async-Await in Rust at a low level is, first of all, the concept of Async-Await and also futures, which is the main feature that's backing it. And then secondarily, this thing called generators, which is the underlying implementation of Async-Await. And then finally, tasks, executors, and reactors, oh my, which is sort of how the futures actually execute. And there's some different parts that are broken up into that. So those 3 things at first are like the most important thing to understand. And the last one is an interesting extension to the language that I personally find really interesting. So it's a little bit more about the future. So let's get into it. First of all, we're going to talk about Async-Await and futures. So first of all, I while I've mentioned this talk is going to have a lot of code and a lot of complicated type signatures, I wanted to show you how you as a user would write code with async-await in Rust. So here's an example taken from Tokyo's docs. Tokyo is a package that implements a bunch of the stuff that we're about to talk about so that you don't have to do it yourself. And so this is a very simple program. You can see on line 6, we have a TCP listener where we listen to a TCP connection on a given localhost port 8080. And then we loop over accepting connections over that listener. And then finally, we do some processing, which I actually sort of eliminated. And so you can see that we got an async function main up here. And we got a couple lines that are marked .await. The question mark is for error handling purposes in Rust. So if you're not familiar with that, that basically says if there's an error, then return the error. Otherwise, return the value. So this is kind of the way that it actually feels when you would be writing normal code with this kind of stuff. You have async functions. You call await sometimes in the body, and you just kind of go on with your day. The main reason people really wanted this is because the ergonomic benefits are pretty massive. This is much simpler than what it desugars to, which is what we're about to get into. But finally, I also wanted to mention that we have this concept called an async block. So you don't actually need to have a full function for async-await. You can also do async and then a curly brace. In this case, the move is there for reasons I don't want to get into at the moment. But you can also take portions of your code and wrap them up in async-await as well. It doesn't actually have to be at the function boundary. And that's useful because in this example, there's this API called Tokyo Spawn, and that basically spins up a new task. We're going to talk a lot about tasks in the future, but sort of the idea is this spins up a new unit of work. And so rather than make you write a brand new function every time, passing an async block to it sort of makes sense. So yeah, this is kind of like what writing code would feel like and the way that most people would interact with async-await. But if you want to start understanding it at a more surface, like a deeper level, the very first thing that you need to understand is that async-await is simpler syntax for writing this thing called future in Rust. There's actually technically an asterisk there. It's a little more complicated than that, but that's like the high-level way to think about it. We're going to get into the asterisk in just a minute. But ultimately, that's really the way that you want to think about it. And a future is this concept that represents some sort of value that will exist sometime in the future. This is kind of the core idea of asynchronicity, but this reifies it into an actual thing. And so instead of needing to have a callback, which may be executed at some time in the future, the idea is you have this object, and Rust doesn't really have objects in the OO sense, but a bit of data that you can basically ask, hey, does that thing exist yet? And it'll either tell you it doesn't exist yet, check back with me later, or it'll say, yeah, it exists, here's the value. And that's kind of this core idea, and so that's the basic principle. And that lets us represent asynchronicity in a way that works really well with everything else. So the first thing we're going to do is build a future. Specifically, we have this example called a timer future. So what's going to happen is this is a future that goes to sleep for a certain amount of time, and then after that amount of time happens, it will sort of wake up and say, here's this particular value. This is sort of a great hello world example of building a future by hand. And while async-await sort of builds futures for you, at the lowest level, people who write libraries will implement futures by hand. And so I'm going to show you how to do that so you can kind of see what the guts look like, because we're going to talk a lot more about the guts. The implementation strategy we're taking for this timer future is very simple. You could write a much more efficient one than this, and that's also true of sort of all of the code examples that I'm going to show in this talk. I'm trying to show examples that are easier to understand, not necessarily the most efficient. So the folks who write libraries that do this for production grade things will be writing significantly more complicated code, but it'll have more performance. So in this case, we're going to put a mutex around a Boolean. And that Boolean is going to live between our future and also a new thread that our future spins up. And that thread is then going to sleep for however long we decide we want to wait. And then when that thread wakes back up, it will set the Boolean to true and tell the future, hey, we're good to go. And calls to the poll method of future, which we're going to talk about in 1 second, will check that Boolean to see if we've waked up yet or not. So this means you have a thread per timer, super inefficient, mutex around a Boolean, also super inefficient. You probably would want to use an atomic integer instead, yada yada. I'm trying to keep this very simple, like I said. A real implementation would integrate with your operating system to set up a timer and do all that kind of stuff. So I mentioned a bunch about futures so far. A future is a trait in Rust. So that means that it's an interface that you can build different things. The interface sort of looks like this. There's two main components. First of all is the trait future itself. It has an associated type called output, and that's the value that you will get from the future if it ever exists. And then there's this function called poll that takes two arguments, itself and a context. We're going to ignore those completely for now. And it returns this enum called poll with the output type. And the poll enum is defined as either ready or pending. So the idea is that we call poll, and then we get back either a thing that says, yes, you're ready, here's the value, or you get back a thing that says, we're not ready yet. You may be wondering about error handling. So previous iterations of this feature had error handling built in, but it's actually easier to compose this with standard Rust error handling idioms. So what happens is if you have a future that can fail, then the output type will be what Rust calls a result, which indicates success or failure. So you kind of compose the result type with the future's return type, and that makes things like a lot cleaner and interoperable. And means you don't need to represent different concepts of like fallible versus infallible futures and like all that stuff. We explored with those designs over the last couple years, and this is basically the cleanest and like most orthogonal way to do it. So let's actually build a future. We're going to build this timer future, so we create a struct to actually represent the data that we need to hold. And inside it, we have this thing called shared state, which has an atomic reference counted thing wrapped around a mutex, wrapped around this thing called shared state. And shared state is going to have two bits of data. First of all, that Boolean that I talked about, which is going to represent whether or not we've like finished sleeping. And then finally, this thing called a waker. We're going to get more into wakers in a second, but we need to keep track of both of these bits of data in this design. And we're going to wrap them up in this arc mutex. Again, sort of for simplicity's sake, this is actually super inefficient. Then when we're actually implementing a future for this timer future, so the output of our timer future is not actually anything. All we're doing is just waking up. And you would usually chain this future with something else. So you'd say like, okay, when this is done, then do something else. So we're not really producing a value out of futures. So there on line 2 where it says the type output is the empty tuple, we're not actually like producing anything. And so finally, like line 3 is that type signature we just saw with poll. And so this is going to be implementation, like what happens when the runtime calls our timer future and actually wants something to execute. Fundamentally, what happens here is we lock the mutex, and it's stored in our shared state, so we can actually look at its contents. And then we check to see like if it's completed, if that Boolean is set to true, then we return that we're ready with that empty tuple. And if we're not ready yet, what we do is we stash a copy of the waker into that shared state. This comes from that context variable up top. So this is specifically like the end of line 9. We're like taking a copy of the waker and we're storing it in our future. And we'll get into specifics about that in a second. You'll see how that stuff interacts. And then we return, hey, we're not actually ready yet. And so this is like a very simple implementation. Like check the bool. If it's good, then we return. If it's not, then we say, hold on, we need to wait yet. And then we actually create our thread that we spin up in a new method. So we say we want to produce a new timer future. So we implement a method on it that takes a certain duration so that we can parameterize how much time we want to wait. And then this is going to end up, so first of all, constructing that shared state. As you can see on lines like 3 through 6, we set our Boolean to false, and we put a none into where the waker is because we don't have one yet because the future hasn't started actually executing. And then on line 9 through line 18 is where we're spinning up our thread. So we're producing a new thread with thread spawn. We pass a closure to it with what we want to execute in the body of the thread. And on line 10 there, you can see that the thread sleeps for however long that duration is that we passed in. And then after it's done, it will take the mutex out on line 11 and unlock the mutex, set that completed Boolean to true. And then lines 15 through 17 are the interesting part with this waker. So we take that waker that we had stashed in our future, and we call this wake function on it. This is a interesting part. I have a diagram later for how all these bits sort of interact, but I decided to wait until after we talked about the future. Basically, there's this concept called a waker, and your future, before it returns that it's ready, it needs to call this wake function to let the executor know that it's happening. We haven't gotten there yet. I promise we will. For now, just like know that futures need to interact with this API, and they have to call wake to like awaken themselves. And then finally, we return the future that we have. And that's it. There's a lot of moving parts going on here. but like fundamentally we have our thread, we have our structure, the thread sleeps, and that's it. You don't need to write stuff like this in everyday Rust because other people have libraries that have done it for you. So this is sort of like an academic exercise, but I sort of wanted to show you the bits and pieces of how these sort of move together, and we're going to build some stuff to actually execute this feature in the future later in this talk. And so I sort of wanted to show you like the very basic implementation of this kind of thing. So yeah. Next up, briefly, I want to take a small detour and give you sort of like 4 rules as a user when you're using Async-Await to sort of get an intuition for how you would actually use it yourself before we dig into the guts of the next like big concept here. So as I mentioned in that joke slide earlier with the they live slide, if you write an async function foo that say takes a string as an argument and returns a 32-bit integer, then that's sort of syntax sugar. And what it's sugar for is a regular function that still takes that string as an argument, but returns some implementation of a future that returns that 32-bit value as its output. And so you can kind of think of like async functions sort of return some kind of anonymous future struct. Why would you not just write that impl future yourself? There's a lot of reasons that we're going to get into in a second, but the point is that mentally this is like how you think about Async-Await as a user, as like an async function returns a future, but I don't have to worry about that. And what that means is if you have some sort of future that you get from a library or from another async function, and you want to get that value out of it, you call await on that future. And so this can work with any future from any source. It doesn't really matter. And sort of that's how you like pull the value out, is by calling await. And then finally, well, not actually super finally, but like you can only call await inside of an async function or an async block because it's building up this chain of futures, which is the next subject we're about to talk about. And so you can't just await on a random value anywhere. You have to do it inside of one of these function bodies, and that's kind of why it's called Async-Await, is because you can't really use await without also using async. And the last interesting one before we get into some more of the details of how the system works. This is the biggest thing that trips people up that are coming from a language like Node.js with their version of promises and Async-Await. And that is futures don't execute until you pass it to something that's conveniently called an executor. So in languages like Node, there is a runtime, and that exists in all programs. And there's this thing called the event loop, which we're going to talk about in a minute. And it sort of executes whatever promises that you build with Async-Await kind of automatically. So as soon as you create a promise, it'll get put on the microtask queue, and then it'll end up being implemented. Rust works a little bit differently in that when you call this async function, you get a future back. Futures don't start executing until you explicitly tell them to. And this is sort of a slight change in mental model, but it leads to some pretty extreme efficiency gains that are not really possible otherwise. And we're going to get into what those are. But before I do that, we said that you can't execute a future unless you pass it to an executor. But when I showed you the code earlier with Tokyo, like there was no executor and passing a future to it. So like, how does that work? Well, there is this magic little attribute that's happened called Tokyo main that lets you write async function main. And basically that's a little macro that takes your main function, grabs a future out of it, and submits it to an executor and then calls wait. So this like means you don't actually have to do it yourself. And you can kind of think of this as more of like a Node.js-y sort of style of writing things. But we've built this as convenience functions in libraries because we don't have like a language built-in event loop. You want to be able to use libraries that have implemented these in different ways, because some people are writing web applications and they don't care about dynamically allocating memory that much, and they certainly care about network performance. Other people use Async-Await on embedded devices, and they really care about not allocating memory dynamically and doing those kind of things. They may not want to be able to have an unbounded queue of possible tasks, because that means more dynamic memory allocation. And so there's a lot of options in sort of the space that Rust is in. So we can't build these things into the language, and that means you end up using these library features to make it more ergonomic. So we'll actually show submitting a future to an executor manually once we actually write an executor in a bit. But there's one last part of this implication that trips folks up that are coming from Node or just JavaScript in the browser even, and that is this sort of example. So here I have this is an actual timer function that someone wrote, so it's called delay instead of the one that we implemented. And I wrote this function called iSleep that basically sleeps for 5 seconds. And so if you write this code where on line 6, we call iSleep once, and then on line 7, we call iSleep again, we get 2 variables, so we have 2 futures, and we wait on them on lines 9 and 10. If you're used to coming from JavaScript, you might think that this function would take roughly 5 seconds to execute, because as soon as you would call iSleep, it would start processing those 2 futures and go around in the background. But because everything doesn't happen until you submit stuff to an executor, and await actually like makes things happen sort of sequentially, this will actually wait for the full first future to happen, and so that'll take 5 seconds, and then it'll wait for the full second future to happen, and that'll take 5 seconds. And so this is a thing that definitely sort of trips people up sometimes when they're getting started. If you want to emulate the node behavior, there's a function called join that will take 2 futures and wait them in parallel. And so if you want parallelism, you need to like expressly put it in the Rust model. So that's like probably the biggest shift coming from something like JavaScript to something like Rust, is that you don't get this automatic execution. And it's extra unfortunate because Rust has this reputation of if it compiles, it works. And so a lot of people coming from JavaScript write their first program with futures, and it compiles, and they run it, and then it doesn't do anything. And they're like, I thought if it compiled, it actually works. And it turns out that if you don't submit the future, like Rust will be like, sure, that computation you're describing, it is typed perfectly. Everything is set up, you're good to go, and then does not actually execute it. So cool, we just return and don't do anything. And that can be a little surprising. So those 2 things in combination are sort of like important to remember. But yeah, the reason that this happens is what I'm about to get into now, which is that because Rust is really interested in type system stuff and efficiency, it means that we do a lot of static analysis of how you're using async and await to build up sort of like the maximally efficient thing that you possibly could execute. So the issue with the model that JavaScript uses, which is great for it as a language, is that in order for the future to start executing as soon as you call it, we would need to actually like allocate that as a task and then start executing it in the background while we create new values. But Rust wants to take your entire computation the whole way through, everything you've chained together, and then compile it down into something super mega ultra efficient. And you couldn't do that if your computation started running before you've even like pieced the whole thing together. And so we're going to talk about how that implementation actually works now. So part 2, generators, also called stackless coroutines. There are like a million different names for the features in this area, and no one has consistent terminology whatsoever. So I sort of apologize. Names are hard. We call them generators. Other people call them stackless coroutines. Some people are like, well, coroutines don't return a value, and generators return a value, so a generator is a kind of coroutine. Whatever. I don't actually care about arguing about names. The point is, we called our feature generators, and it's fine. Generators are not a stable feature of the Rust language yet. They're in nightly, and you can try playing around with them, and so I'm going to show you as the nightly only syntax, but I'll make it clear that you can't actually implement generators by hand on stable Rust yet. If you are watching this talk a year from now, maybe this all has changed. I just want to like flag that as a thing, but it's important because generators are how Async-Await is implemented under the hood, so that's why we put them in the language, is because the compiler uses this feature to do that efficient computation-based stuff I was talking about. So in order to truly understand the details, you kind of have to know a little bit about this experimental feature. At its core, generators are sometimes called resumable functions. I never really thought that made sense to me. If that makes sense to you, awesome. Basically what happens is in Rust's case, we make this generator and it looks like a closure. So you have the 2 pipes, this generator takes no arguments, and in this case we're taking a vector of numbers 1, 2, and 3, and we're summing them up, but we're returning the intermediate results each time. So you can see there's this for loop where we add the current value onto the sum, and then we yield sum. And so what happens is when you invoke gen for the first time, it will basically run up to the yield and then return that first value, and you get the value back. And then you can invoke the generator again, and it will continue processing execution and then run through the second iteration and then return the second value, and then again and again and again. That's why it's called like a generator, is because you're generating these sequences of values. And fundamentally how this works is it looks like a closure, but you put yield in there. This is a feature that's in a lot of languages with a lot of names. I used Ruby, so this kind of made intuitive sense to me, even though we never called them generators. But yeah. Here's a slightly more complicated generator that basically does the exact same thing. We're going to be first adding up all the numbers, and then secondly, subtracting all the numbers by going back down. And the reason that I wanted to use this slightly more interesting generator is I want to show you how Rust actually compiles this generator into efficient code behind the scenes, and we needed something a little more complicated than just one yield. So we kind of have, if you would think about how you would try to implement a feature like generators, fundamentally you need to save the intermediate state that happens between producing each value. So what happens here is on line 4, we have an iterator. Iterators have internal state. So we mark this with this comment iter0. So we're going to need to save, up to the first yield, we're going to need to save the value of this particular iterator. And then on line 6, where we yield that sum, we also are going to be giving this value back, and that's going to be like sort of the starting value for the next iteration of the computation. So we're going to need to save both the state of the iterator and the value that we yielded in the sort of first step through the generator. And then likewise, lines 8 and 10, when we reverse through the iterator, we're going to need to save that at every single step, and we're going to need to save the sum the second time. So we kind of have these like 2 big sections of yield with 2 little bits of state in between them. And so the way that Rust builds this, you can actually think about it in Rust code. So there's sort of these like 4 stages as we pass through this state. First of all, there's the like generator that we've never called, like we've never actually asked to execute, and that holds this state of a list of 32-bit integers. And then after we call it for the first time, we move from this unresumed state into this suspend state. And so now we still have our list of vectors, our vector of integers, but we also have that iterator, and we have the intermediate sum. And then after we like totally exhaust that, we move into the suspend 1 state, and that means we have similarly, we need the list that exists and the iterator that's going backwards now, and the current sum state. And then finally, once this computation is done, there's this return state here. And so there's this really deep, like there could be a totally different talk on this computer science-y track about how like coroutines and generators, if you squint at this, like it looks like a state machine, right? Like we're progressing through these states, and there's a really beautiful underlying unified theory of computation that puts all these things together in a wonderful way. I don't have time to explain. But basically, like generators are kind of this really convenient way to write a state machine, and this is kind of what the state machine would look like desugared. And what this means is that the generator has sort of like a maximum, because this is an enum of like structs, the generator has sort of a maximum size in memory of the biggest chunk of state that you need to save at any given point of the computation, but we can reuse that space for the smaller ones. And so you get this really compact, nice and tiny representation of the value, which is really efficient, and that will become important later. So anyway, that's a quick whirlwind summary of generators and kind of like what the code they generate looks like. But the way this interacts with futures and Async-Await, excuse me, futures need to have a poll method that's called over and over again until some sort of value is produced. Generators let you call, like invoke them, and then they yield a value over and over to get this sequence of values. So there's sort of this interesting symmetry here, and that's why Async-Await is implemented internally as a generator that implements the future trait. So basically Async-Await is a simpler syntax for not just futures, but more specifically a generator that implements future. And so that's like, you can think like these state transitions come from the values that are returned by the calls to poll, and everything sort of fits all nice together. And that means that we can take your entire chain of Async-Await computation, compile it down into one single state machine that represents that whole entire chain of computation, put in a very compact representation, and know at compile time, basically like exactly the size that that computation will take. So we call these stackless coroutines because they don't allocate their own stack, but you can kind of almost think about like stackless coroutines as like perfectly sized stack coroutines. Like we don't need to allocate every single like iteration through, like I said, what happens with JavaScript. We can instead get like the exact size that's needed for the whole computation all at once at compile time and be perfect. And this is one of the reasons why Rust's implementation is a little novel, and also why it's super, super highly efficient, because like you can't actually hand code it better yourself. Now, there's definitely some optimizations that we're missing when it comes to compacting the generator state, and so there still is better work to be done. I also want to set some like expectations there, but like in a theoretical sense, we're basically doing as much processing at compile time as you possibly can to make this as zero overhead as possible, and that's really cool. All right, so next up, we know how we use futures, how we implement futures ourselves, and we know how we can use Async-Await to work with futures. But as I said, in order for a future to execute, you have to put it on an executor. And so now we're going to talk about the last sort of remaining part of the system, and also another part that's interesting due to some other splits, and that's the tasks, executors, and reactors chunk of this story. So generators and futures and async-await are all in the Rust language, but as I mentioned before, Rust doesn't have like a built-in executor, and that's because Rust is used in many different contexts, and we need to give people choice. And there are some people that don't even need asynchronous computation, and we don't want to have them have to pay for this stuff if they don't need it. And so the way this kind of works is that the future trait is in the standard library, and async-await and generator, well, the future trait and generators are in the standard library. Async-await is in the language, but all the ways that you actually execute that is left to the library ecosystem. So I showed you Tokyo before. There's a number of other projects that are providing different kind of executors and reactors that do different things for different areas, and some of them are competing to be the best one for web apps, and some of them are doing embedded and like all these other things. So what I'm about to show you in this section is an implementation of a simple executor, but again, like the folks who are building the real libraries that use in production do a lot of tricks to make this much, much faster. So I'm trying to emphasize for like learnability, not for ultimate speed. But that's the nice thing, is that you can kind of build one of these things yourself and use it in your toy program and then rip it out and replace it with a production ready one, and now all your stuff just goes faster. Interfaces are awesome. So Node has this thing called the event loop. And I bring up Node in this talk a number of times because Node was probably the primary inspiration for how we did all this stuff. A lot of people in the Rust world were JavaScript programmers before, and Node kind of like made this sort of style of programming kind of like cool, even if it didn't pioneer it ultimately. And so I tend to compare against Node because that tends to be what people know in this space. But Node programmers will talk about the event loop, and that's sort of this thing that makes your asynchronous computation happen. And whether or not you're like just a regular person writing Node code, you don't want to think about how the event loop works, and all you know is like don't block the event loop is like a meme, and you try not to do that. Or if you're someone that's like on the Node TSC and you're a contributor to libuv and you like know about all the guts, like they talk about it in one sort of like unified way. Well, in Rust, because we don't have one guaranteed thing that went with the language, we actually broke it into sort of 3 different concepts, and we're going to use a 4th minor one later. But when we talk about asynchronous sort of work, there's this idea of a task. And so in the case of Rust and async-await, a task specifically represents some sort of chain of futures that you've made into a computation, and you're like, I want to actually execute this thing now. So you hand a task off to an executor to be scheduled and run. And so the executor is basically just like a scheduling algorithm, and it takes a list of futures that it knows needs to run, and it figures out how to run them. Because there's all sorts of different strategies you can use. We're going to use a very simple one that's based on a first in, first out queue. There are other people that do like multi-threaded work stealing executors and like all these other kind of things. So there's a lot of space to explore with how to schedule work that are good for different workloads. And then finally, there's this concept called the reactor. And this would be what like libuv is in Node world. Basically, it's the thing that notifies the executor which tasks are actually ready to continue executing. And so this often is tied with a specific operating system UI. And we sort of split these things apart conceptually, even though a lot of projects provide both. So for example, Tokyo gives you both an executor and a reactor. But in theory, you could actually like pair Tokyo's reactor with a totally different executor if you didn't like their executive decisions. But they're like separate things, whereas all this is kind of bundled up into one thing in many other systems. And that gives us flexibility, but that also means intense type system stuff. So we sort of ignored these some of the details about the call to poll earlier. But if you read the type signature, you can kind of see how this works with the executor and reactor. So if we take a future and like tasks implement future, which is when you pass a task to an executor, the executor's job is to do that repeated call of poll. So it's going to be calling poll to make sure that your futures are doing the work they're supposed to do. And it gives this sort of context argument to futures. What this context argument actually is was the source of a lot of the situation of developing the future trait. But what it currently contains at the moment is basically that interface into the reactor. So that waker concept I referenced before, that's like put the executor is like, okay, you're using this particular reactor. I bundle up in this context, and I pass it along to the futures. And so that's how the future is able to interact with the reactors through that waker interface, and that's part of this like context chunk of stuff. There's like 4 levels of indirection here, so it takes a little while to get synced into this. Honestly, one of the reasons I wanted to do this talk was to force myself to walk through all these details and make sure that I got it, because I knew it at a high level before, but I wanted to do a bunch of the research. So yeah, so like an executor calls poll, it gives you a context, and that context contains a waker, and that waker is how the reactor talks to a future. So let's actually build an executor together. I'm going to show you a very simple executor that, again, is super inefficient, but like actually works. Before we get into the code, though, we're going to do a good old-fashioned flow chart of all these bits and pieces because, like I said, there's a lot of moving bits around here. So if we have an async function foo that we want to turn into a task somehow, we are going to call this interface called spawner and spawn foo. If you notice, there was that API in Tokyo, and the first thing that had Tokyo spawn that lets you like spin up a new task. So tasks can also like produce new tasks, and sometimes those are nicknamed spawners. You don't have to make them a whole separate thing, but we're about to do that in our particular implementation. So we sort of hand foo off to this interface that says, please make a task out of the results of foo. And from there, that is going to send it to the executor, and in our case, we're going to have a queue of tasks. So we're going to put things into this queue, and the executor is going to go through the queue and execute each task in turn. So it's going to hold on to that state. When the executor calls poll on a future that happens to be in its queue, that's what it's going to do, to execute the future. Call poll and see what happens. And that future will return either ready, and then it'll be done, and the executor will remove it from the queue, or it'll say that, hey, I'm not ready yet, and the executor will say, okay, and it won't keep that in the list of things it needs to poll, and it's basically going to say, I'm not going to call poll again until I'm told that you're ready to continue executing. This is where the waker bit comes in. And so at some point, whenever the future is ready, it's going to call wake in the background. If you think back to our timer future, this happened in that background thread, so that's why this keeps happening. Like you may wonder, like, if the executor never calls poll again, how am I supposed to even run the code for the waker? Well, it depends on what you're doing. In our timer example, it was that background thread. If you were building a full-blown reactor, it would maybe be like epoll you've handed off a callback to epoll that's going to like invoke the waker when that happens. But in some sort of way, the future is going to be told, hey, I'm ready to proceed, and it's going to wake up. And that's going to cause the future to be re-put onto the ready queue of the executor to be executed again. So this is kind of the basic control flow of how the system works. So let's actually put one of these things together. So as I mentioned, we have our executor and it has a ready queue. And this is going to have, basically, there's going to be a channel. That's what the receiver part is we're going to be sending things to the executor over this channel, and we're going to treat our channel like a queue because you can do that. So when people put stuff on the channel, like a channel maintains an internal queue, and we pop things off. So we're basically just going to like keep listening to a channel to implement this particular queue, and it's going to get a reference counted task. A task contains the future, and this has a frankly kind of bonkers type signature, a mutex option box future of static and then no output. Box future is itself a type alias. This could actually go 2 or 3 more nested types. Types are happen at compile time, not run times. The more types you put together, the more compile time stuff happens and the faster everything is, right? Isn't that totally true? But the point is that we need this to be thread safe, and actually we don't even need the mutex here because we're not building a multi-threaded executor, but Rust sort of forces you to make your code thread safe to begin with. If we were making a single threaded executor, we could eliminate the mutex with some unsafe code, but I'm trying to make this simple, not complicated, so it's some overhead that we wouldn't actually need in production. Don't worry, your futures are not all wrapped in mutexes and boxes and stuff. And then finally, a task is also going to have the other end of that channel. So when a task needs to reschedule itself, it's basically going to like send itself down this channel. So it needs a reference to it so it knows where to send it. So that's the other component of our task and executor. Then to make it a little easier to spawn tasks on the executor, we're going to split out the spawner type. You don't have to do it this way, but it can be kind of easier to send the spawner around rather than moving the executor everywhere. And it holds the other end of this channel that is in the executor. So the sender sends stuff down the channel, the executor pulls stuff off the channel, and then actually runs the futures. And we made this little helper function called new executor and spawner that spins up an executor and spawner that know how to talk to each other. And in this case, because we're using this particular kind of channel, we're going to give it 10,000 tasks maximum because this is a toy. Again, most real ones will give you a queue that is like unbounded if you want that kind of behavior and like all this sort of different stuff. So yeah, so this is how we'll get our executor and spawner. Spawner is relatively straightforward. What we need to do is we need to take our future, which is the task we're going to create, we box it up, and then we put it inside that arc, and we give it that reference to the particular channel that we're sending stuff down, and then we basically send it down the channel as like, hey, this is ready to execute. Pretty relatively straightforward. And then finally, we implement this the wake method on our task. So in this case, this would be like where you would put more complicated logic if you were doing something that interacted with the operating system. But here, what happens is whenever a future calls wake, what we're going to do is send it back down to that channel to be executed immediately. So we kind of created a very simple system by which, like, anytime you call wake, we're not going to sleep anymore. We're going to immediately re-queue you to be executed. And then finally, here's the guts of the executor itself. This is the last big chunk of code slide. But an executor fundamentally is a while loop. So we have a while loop, and we receive stuff off of our queue there on line 3. And when we get something off of the end of the queue, we have that task, and then we use the mutex to grab access to it. And we take the future out of this particular slot in the task because we want to see like if this future still needs to be executed or not. So when the future is done, we'll no longer have the future anymore. So we have to double check if it's finished or not. And so that's what line 8 does, is like check to make sure, hey, does the future still exist? If it does, we want to rip it out of the task. Lines 10 and 11 set up that waker. So we're taking the particular waker that we implemented, and we're turning it into a context, because that's what needs to be passed to a particular future. And then finally, line 13 is where we call poll, we pass in that context, and we see what happens. If it's appending, then we're still processing the future, so we need to put that future back in the task since we ripped it out before. So we re-put that back in, and we're good to go. If the future is done executing, we don't need to put anything back in, and we're just finished. And that's really it. Like, this is just ultimately the guts, as I said, of the executor. You loop over the queue, you run the futures, you check what they're doing, and that's it. So this is like a relatively small number of lines of code, but it would let us actually implement our own async-await stuff. So here's an example of using this executor we just defined. So we call a new executor and spawner to get a new executor and a new spawner. We call spawner.spawn, and in this case, we're going to use that async block to just print a message, sleep for 2 seconds, and then print another message. And then finally, on line 15, we're going to drop the spawner. And the reason why is to tell the executor we're done. Our executor implementation will like wait until the channel closes, so it'll always sit there. So if we don't actually like tell the spawner we're done spawning tasks, it would just sit there waiting for tasks forever, and our program would like hang. And then finally, we call run on the executor, and it will take that task that we added and do its magic and run it. So this is kind of like the minimal code example of how to put all these bits together, and it kind of shows you how the control flow works through the system and the way that all these different parts work together. Okay, we didn't talk about pin. Pin was part of the function signature of the future. If you notice, it said pin self, and we didn't talk about it. Pin deserves its own whole talk. It's kind of really interesting and complicated, but basically the idea is before a future starts executing, we need to move it around in memory. So for example, to create a task out of a future, we often put it on the heap, so we need to move it from the stack to the heap, which involves moving it in memory. The problem is Rust is a systems language, it doesn't have a garbage collector, so we have pointers. So if you move something where there's pointers that exist to the thing, you're going to invalidate those pointers, and everything's going to blow up. So that's not great. But the problem is once a future starts actually executing, it can't move in memory for like similar reasons. So like before it moves, we need to be able to, before it executes, we need to move it, but after it starts moving, it can't move at all. Because again, if it moved, it would cause all these references to be invalidated. And the Rust borrow checker really doesn't like sometimes you can move stuff and sometimes you can't. And so somebody had, without boats specifically, came up with this idea of the pin type. And what pin basically says is, hey, once you construct a pin out of a pointer, it will no longer move forever. And so this lets us have stuff that's like not pinned at first, and then part of the job of the creating a task is to actually like pin that future into memory to say, hey, this is going to live here forever, so you're free to start executing yourself. There's also a type called unpin that basically says like, I am not a pointer, I don't care about being copied around. This is very similar to how copy says that they don't care about move semantics in the rest of Rust. So that's really all I have to say about pin today. Pin is something you'll virtually never use unless you're building a specific low-level feature by hand. And so it's kind of complicated, but you just don't have to think about it basically ever as a user. But the people who write your libraries do. So I didn't want to leave that out. OK, finally, we have 6 minutes. Let's build a reactor. Just kidding, we're not actually going to build a reactor. Just kidding, we technically did build a reactor. So our reactor was very dumb, and all it did was immediately be like, yes, you're going to start executing again. But this part of implementing the wake trait is where a reactor would fit into this hierarchy of stuff. If you didn't want to say sleep, you wanted to wait on epoll or do whatever, that's sort of where this wake machinery comes in, and that's the part of building reactors. So we did technically write a one-line like no-op reactor, but I'm not going to get into a complicated one because frankly I've shown you far too much giant code blocks in this presentation anyway. There's no other really way to do it without getting into the details, but you know, this could be its own whole thing, right? This is basically like a how to implement libuv talk. Or we actually don't use libuv ourselves. We use a library called, Tokyo uses a library called Mio, which stands for Metal.io, which is kind of like a libuv competitor, blah, blah, blah. The point is there's a lot of rich, interesting problems here, and I will never do it justice, so we're just going to leave it at that for this talk. I have 5 more minutes, and so I'm going to go over the bonus round because I do have time because I think it's really interesting. And I talk about some of the future extensions to Async-Await and how you may hear people talk about type theory questions and you may wonder how it's like relevant to you as a programmer. And this is the easiest way that I can explain it. So async functions and traits. Right now, as of last week, you can write async functions in Rust. But if you want to write a trait with an async function, you can't. And that feels really weird and awkward at first, because you're like, what's the big difference between a function in an interface as opposed to a function outside of an interface? Well, the core of it comes down to a function is just one single function. It's not a big deal. But a trait is implemented on many types, and so ends up being many functions. And as we know, when you go from one of a thing to as many things as you'd like, that's where complexity always creeps in. And so this is where the type system complexity ends up being a thing. We haven't built the type system machinery to handle this situation yet. And you may ask, like, well, why does that matter? Well, if we think about what, like, here's a trait called foo that has an async function called foo that returns a 32-bit value. If you wanted to think about how this would like desugar in the same way that we talked about how async functions desugar into something that returns an implementation of a future, it would look like this. So we'd have an associated type that would be a future of some kind, and you know, it would return that associated type. So this would kind of be syntax sugar for that. This is fine, and you can actually do this today, but the problem is that it only would work for extremely simple things, and it gets way more complicated. And the reason is lifetimes. Always in Rust, lifetimes end up complicating everything, which is like why the language exists, but also is like lifetimes. So if we think about a more interesting trait, so say we have a database trait that will fetch users, we're building an ORM, and want to get a user out. You'll notice that we're borrowing self here. So that borrow means there's a lifetime. And so that means that unlike our very simple example where an async function desugars into just return impl future, we also need to add the lifetime in here. So it's actually like an impl future that refers to the lifetime of self. That's where the root of all these problems come in. Because the problem is if you would desugar that into the general trait, like as I talked about before, now we have a type that's parameterized by a lifetime that implements a future parameterized by a lifetime. And there's no way currently to parameterize an associated type. And you may have heard people refer to associated type constructors in Rust, or maybe generic associated types. This is basically the thing that you're talking about. You can't make line 2 generic in today's Rust, but due to lifetimes, if you would write any useful trait that would be asynchronous, it needs to know what the lifetime is, and so it needs that feature, so that doesn't exist yet. So this is the core reason of why async function doesn't work in traits. We need more type theory shenanigans, and other people who are smarter than me are going to go do all that, and I'm just going to write async function in a trait and be like, ah, it works. Because it actually gets even way, way more complicated than that, but I'm not going to get into that stuff. What I am going to tell you is if you want to use async functions and traits today, you can use this package called async trait, and it implements it for you. It implements it for you. You're like, how does it not exist in the language, but a library can implement it? Basically, what happens is you add this async trait thing onto your trait, and instead of desugaring it into that thing with the associated type, it gives you a box. So it's going to box every single invocation. So the downside you pay for using this library is your futures are a little less efficient because you're allocating every single future. But the advantage is you get to have traits that have asynchronous functions. OK, I have 30 seconds left. Thank you so much for listening to me ramble about how all these bits and pieces fit together and how all the types work. Hopefully you understand a little bit more about how Async-Await is actually generated and how futures are executed. The slides will be posted up on InfoQ later, but I have these 3 blog posts that are really good and go into the examples that I showed you in more detail and with written words, and I really recommend reading them to sort of get additional context on how this stuff works. So thank you so much.